Welcome everybody to day 2 of this SYCL tutorial. My name's Rod Burns, I work at Codeplay Software, and I'm pleased to introduce you to today's session. Today we have some talks from Codeplay, Xilinx, Intel and Heidelberg University, who are the authors of the SYCL implementation. We have 3 different blocks of talks. And between each block of talks we'll have a live question and answer session with all the speakers and a few other people. If you could please post your questions on the Slack channel either during the talks or during the Q&A sessions, and we can hopefully cover some of them there. If you're missing the Slack channel, there's a link to that in the YouTube description. Afterwards we can also try out the unified shared memory hands-on coding exercise. There'll be some time for that after everything's finished. This is a new feature and there's a talk about that by Igor at 5 p.m. GMT. So let's kick off with the first presentation.
Hi everyone, welcome back to part 2 of our SYCLcon SYCL tutorial, Application Development with SYCL. My name is Gordon Brown, I work at Codeplay, and in this talk I'm going to give you a brief overview of our SYCL implementation, Compute CPP. For those of you who are not familiar with Codeplay, we're a small company of approximately 70 people based in Edinburgh in Scotland, and we specialise in developing high-performance heterogeneous computing solutions for accelerators. We develop a full stack for AI and image processing applications, all the way from TensorFlow and other applications all the way down to optimized OpenCL implementations. We are also involved in a number of open standards, including OpenCL, SYCL, SPIR-V and ISO-C++. So in this presentation I'm going to cover what Compute CPP is, a little about the projects that make up the SYCL ecosystem that surrounds Compute CPP. I'll explain the single and multi-compiler solutions and how to use them with Compute CPP. I'll cover how to compile for different targets. And finally, I'll go over some of the extensions to SYCL 1.2.1 that are available in Compute CPP. So what is Compute CPP? Compute CPP is a commercial implementation of SYCL. It supports a number of platforms including Intel, AMD, NVIDIA, Renesas, Imagination, and Codeplay's Aorta. Though note that support for NVIDIA GPUs is still experimental, and support for AMD GPUs does not cover the entire range of devices, so please see the developer documentation for exactly which devices are supported. Compute CPP is also the first conformant implementation of SYCL 1.2.1, which means that it fully implements the specification and it's passed the Coronis Conformance Test Suite. It also provides a number of extensions to the SYCL 1.2.1 specification, which are pushing the future revisions of the SYCL standard. Finally, Compute CPP also supports a fully optimized stack, including TensorFlow and other applications, all the way down to our Compute Aorta OpenCL implementation, which we optimize for customer hardware to achieve optimal performance on their platforms. So there are 2 versions of Compute CPP available. There's the Community Edition and the Professional Edition. Compute CPP is fully supported with the Community Edition, which is available for free for evaluation purposes, and this includes all extensions and integration with the entire ecosystem. But with the Professional Edition, as well as having a license to use Compute CPP for commercial purposes, you also get access to a number of additional features, such as ahead-of-time compilation, tracing, and runtime configuration to get the best performance out of the SYCL runtime. So here we have the SYCL ecosystem which surrounds Compute CPP. So in the middle we have Compute CPP, which provides support for the host device and an OpenCL backend, which supports SPIR, SPIR-V and experimental PTX compilation. On top of Compute CPP, we also have a number of open source SYCL projects, including an implementation of the C++17 parallel algorithms, SYCL BLAS, which is an implementation of the BLAS linear algebra routines, SYCL DNN, which is a neural network library of convolutions and matrix-matrix operations for machine learning, and a SYCL port of Eigen and TensorFlow. There's also the Compute CPP SDK, which is an open source project which provides a number of SYCL sample codes, as well as a full CMake integration, which allows you to find Compute CPP and seamlessly add SYCL support to your projects with only a few commands. So one of the features that Compute CPP provides that I'd like to show you is how it supports both single compiler and multi-compiler solutions for compiling your SYCL applications. First, I'm going to show you how the multi-compiler solution works. So you have a SYCL device compiler, which will compile your SYCL application and output an integration header, which contains the device binaries for your kernels and all the necessary metadata. Then you have a host compiler, which compiles your application again as a standard C++ executable, including the integration header to embed the device binaries into the executable. The benefit of this approach is that you can use any standard C++ compiler as your host compiler, which makes it easier to integrate SYCL into an existing toolchain. The way you compile an application with this approach is first to invoke the Compute CPP device compiler, Compute++, with -SYCL, and have it generate an integration header, a .SYCL file. Then you compile your application again with your host compiler of choice. Here we're using GCC, and you force include that integration header when you compile it. And this will generate an executable that contains both the host application code and the device binaries to be executed at runtime. Now I'm going to show you the single compiler solution. Here, the SYCL application is compiled just once by a SYCL device compiler, but the compiler will perform both host and device compilation phases. For this, the Compute CPP SYCL device compiler provides a SYCL driver mode, which will perform both the host and device compiler invocations and manage the integration of the generated binaries automatically. Now this approach is simpler as you just have a single compiler to work with and there is no need to manage the integration header. However, you do need to replace your existing compiler with the SYCL device compiler, which makes it harder to integrate with existing toolchains. The way you compile a SYCL application with this approach using Compute CPP is to simply invoke Compute++ with your source file as before, but this time with the SYCL driver option. The result of this will be an executable that contains both your application code and your SYCL kernels, which can be invoked at runtime. The Compute++ SYCL device compiler also allows you to specify the target binary format that you wish to compile for. The default is SPEAR, but this allows you to also opt for SPEAR-V or PTX, which is used for the experimental NVIDIA GPU support. To do this, you simply include the SYCL target option when invoking Compute++, as shown here. This will then create an integration header with a SPEAR-V binary containing the kernel functions. With the Compute CPP Professional Edition, this option can also be used to provide multiple targets and have them all contained in a single integration header. It also allows you to do ahead-of-time compilation, which means compiling directly for an instruction set of a specific architecture, such as x86. Finally, here's a list of some of the extensions that we provide with Compute CPP. Firstly, there is the extended dataflow model, which includes host tasks and interrupt tasks. Host tasks allow you to enqueue native C++ functions to be scheduled by the SYCL runtime following the same data dependency model as kernels. This is useful if you want to create callbacks or integrate with other C++ libraries within an asynchronous workflow. Interrupt tasks are similar to host tasks as they also invoke native C++ functions. However, they also allow you to retrieve the native queue and memory objects available at that point in order to integrate with the backend's native API. Compute CPP also has a work-in-progress implementation of the Intel extension for unified shared memory, which allows you to allocate memory in a unified address space. Now, there will be another talk later today that will explain this in more details. We also provide support.
Hello, my name is Igor Voroptsov and I'm a tech Hello, my name is Igor Voroptsov and I'm a technical consulting engineer from Intel. Today we are going to have a short introduction to Data Parallel C++. We will address following topics, starting with a question: what is DPC++, learning a compilation and execution flow of a DPC++ application, and getting some directions on how and where to get a compiler. After day 1 session on SYCL language, I expect that all of you have an understanding on what SYCL is. It can be summarized as a C++ single-source heterogeneous programming for OpenCL in accordance with the current SYCL standard, which is managed by the Kronos group. So by standard, SYCL is a cross-platform abstraction layer. Data Parallel C++ is a high-level language designed for data parallel programming productivity. It is based on C++ for broad compatibility and uses common familiar C and C++ constructs. The language seeks to deliver performance on par with other compiled languages, such as standard C++ compiled code, and uses C++ class libraries to allow the compiler to interpret the code and run on various supported architectures. DPC++ is based on SYCL from the Kronos group to support data parallelism and heterogeneous programming. In addition, Intel works on extensions to SYCL with the aim of providing value to customer code and working with the standards organization for adoption. For instance, the DPC++ language includes an implementation of unified shared memory to ease memory usage between the host and accelerators. These features are being driven into a future version of the SYCL language. You can take a look for a full list of additional features on Intel GitHub project with a detailed description. Note that all of SYCL is included in DPC++. Let's talk about some DPC++ implementation details. As I said, it is a C++ language and it doesn't introduce new keywords, so from the syntax point of view, it is a regular C++. The C++ is extended to DPC++ via the template library. It is a set of header files required for compilation and the runtime. The front end of a DPC++ compiler is based on the CLang, as well as a backend is based on LLVM framework. There is an open source DPC++ compiler initially created by Intel available from a GitHub repository, and you can build the DPC++ compiler using available sources. There is also a commercial version of a DPC++ compiler available in binaries as a part of Intel One API toolkits. All the features of DPC++ and SYCL are supported by both the open source and commercial versions of the DPC++ compilers. Goal of DPC++ open source project is to merge with top trunk of LLVM and CLang. You can find an Intel Graphics Compute Runtime for One API Level 0 and OpenCL driver following this link. It is also an open source project which provided Compute API support for Intel graphics hardware architectures. Neo is the shorthand name for this compute runtime. It currently supports Gen 9 and later graphics devices. Now, let's talk about DPC++ compilation and execution flows. Compilation module supports code that executes on both a host and accelerator or several accelerators. In that case, commands issued by compiler, linker, and other supporting tools are obviously more complicated than usual C++ compilations. However, DPC++ compiler hides this complexity for us by default and just works out of box. Here is a simple example of a one-source file compilation process. You may compile it using a DPC++ compiler driver with a single compiler command. Usually, at least two compilers are invoked under the hood. One is a host compiler, and the other one is a device compiler. With default options, the output for device code is an intermediate form. At runtime, the device handler on the system will just-in-time compile the intermediate form into code to run on the device. Since we have a single source code which combines both the host and device code, it is natural to want a single executable file to be the result. The linker merged both binaries generated by host and device compilers to a fat binary. In our example, the device code in a fat binary is an intermediate form that defers the final code creation until runtime. To be more specific, it is a SPIRV binary format. There is also an option to do a target-specific executable code, and we will cover it in the following slides. Once you have your fat executable, you want to execute it on some device. A DPC++ runtime consists of two parts. High-level SYCL runtime, which for example should care on data dependencies by creating a dependency graph and scheduling kernel's execution order, and a lower-level runtime, which should map high-level abstractions to the real hardware commands. DPC++ uses a plugin interface to target different backends. Intel provides an OpenCL plugin that enables DPC++ to run on OpenCL platforms at this moment. However, there is also a Level 0 API specification available which provides direct-to-metal interfaces to offload accelerator devices. While initially influenced by our low-level APIs such as OpenCL, the Level 0 API are designed to evolve independently. There is also a plugin implemented by Codeplay that adds the support for NVIDIA to the DPC++ compiler, and it is based directly on NVIDIA CUDA rather than OpenCL. It can be selected at runtime by setting the environment variable SYCLBE. So DPC++ is not limited to use an OpenCL low-level APIs as a backend. We already talked about one-file compilation flow and covered some execution basics. This picture summarizes it and shows a full compilation and execution flow of DPC++ application. The DPC++ compiler generates an intermediate representation that can be just-in-time compiled to a specific target at runtime. Or it can generate target-specific executable code similar to traditional C++ compilers ahead of time compilation. DPC++ supports ahead-of-time compilation for Intel CPUs, Intel processor graphics Gen 9 or above, and Intel FPGAs. To use the AOT feature for targeting a GPU, you must have the OpenCL offline compiler installed. You can find more details following this link. Now, let's talk about where and how to get the DPC++ compiler. There are several ways how to get it. The easiest one is to use a pre-built compiler shipped through one of the OneAPI toolkits. An alternative is to use a dev cloud with already installed tools on a variety of supported hardwares. There is also an option to build the compiler sources from a GitHub project, but you will anyway want OneAPI toolkit because there is a set of useful tools there. The Intel Dev Cloud is a development sandbox program DPC++ cross-architecture application. You can sign up for a full access to the latest Intel CPUs, GPUs, and FPGAs with the installed Intel OneAPI toolkits. Intel offers many toolkits, but there is a core set of high-performance tools for building data parallel C++ called Intel OneAPI Base Toolkit. Other add-ons toolkits targeting specific developer workloads that build on the core toolkit. For example, in OneAPI HPC toolkit, you may find additional HPC tools like Fortran compiler. You can download toolkits for free and find more details on each toolkit at software.intel.com/OneAPI. As a summary note, a DPC++ delivers power and productivity of modern C++ and leverages SYCL standard to support parallelism and heterogeneous programming. Thank you for your attention, and now we are open for questions.
Hello everybody, welcome to this introduction to HipSYCL. My name is Axel Alpay, I work for Heidelberg University and I lead the HipSYCL project. HipSYCL is an open source SYCL implementation led by Heidelberg University. You can go check it out on its GitHub page. Unlike other SYCL implementations which rely mainly on OpenCL, HipSYCL is built on top of OpenMP, CUDA or ROCm with no additional layers in between. In HipSYCL, we rely on the Clang, CUDA or HIP frontend with an additional HipSYCL Clang plugin to add support for SYCL constructs. Because of this architecture, since the code still goes through a HIP or CUDA toolchain, kernel performance can be expected to be on par with Clang compiled CUDA or HIP by design. In addition, the HipSYCL compiler understands not only SYCL, but also CUDA or HIP, so you can really mix and match SYCL and CUDA or HIP code in the same source file. And this allows you to create highly optimized code paths for specific devices. It also gives you full CUDA or HIP interoperability and allows you to use vendor tooling, optimize vendor libraries, CUDA or HIP template libraries, even the latest device intrinsics, and so on and so forth. If you want to install HipSYCL, the easiest way is to use our package repositories. We provide Debian, RPM, and Arch Linux packages, not only for HipSYCL itself, but also for matching LLVM and ROCm distributions. There are also some community-provided packages. For example, there is a spec package for the CPU and CUDA backends. The ROCm backend is not yet supported. There are also ongoing packaging efforts in the communities of Gentoo, NixOS, and the Arch Linux AUR. If you use spec, then installing HipSYCL is as easy as typing spec install HipSYCL at master plus CUDA if you want to have CUDA support. Of course, you can also install it from source. This is also documented on the GitHub page. If you compile code with HipSYCL, you use the SYCLcc compiler wrapper. It's also sometimes referred to as SYCLcc Clang. It's exactly the same thing. You can either type SYCLcc or SYCLcc Clang. It makes no difference. SYCLcc hides all the nasty details. For example, how to invoke the compiler correctly, how to load the HipSYCL Clang plugin if it needs to be loaded, linking against HipSYCL, setting the correct include paths, and so on and so forth. SYCLcc behaves exactly like a regular C++ compiler, so you can use your regular optimization, C++ optimization flags and any other flags that you can use, for example, for Clang, you can use with SYCLcc. In addition, SYCLcc provides a couple of HipSYCL specific command line arguments, such as --HipSYCL platform, which can be used to set your target platform to CUDA, ROCm, or CPU, depending on what you're targeting. If you're targeting GPU, you can also use --HipSYCL GPU arch to set your target GPU architecture. And if you're compiling for CPU, you can use HipSYCL CPU CXX to set your CPU host compiler. You can do all the same settings also with environment variables. However, if both command line arguments as well as environment variables are provided, the command line arguments take precedence. And if neither are given, then SYCLcc will just use some default settings from some configuration file that is installed when installing HipSYCL. If you don't want to use SYCLcc manually, you can also use our CMake integration, which allows you to just find package HipSYCL and then use the function add SYCL to target. This function is also provided by other SYCL implementations, which means that you can use the same CMake code to target many SYCL implementations. Since SYCL is pure C++, it can be implemented as a regular C++ library if you're only interested in targeting CPU. And this is how we have implemented the HipSYCL CPU backend. So for the HipSYCL, when compiling for CPU, you don't need a special compiler in HipSYCL. You can use your favorite CPU compiler as long as it supports OpenMP. This decision, however, is done by SYCLcc. So if you tell SYCLcc that you're targeting a GPU, then SYCLcc will invoke Clang with the HipSYCL plugin behind the scenes. If you tell it that you're targeting CPU, then it will invoke your host compiler that you have specified. One of the most interesting things about HipSYCL is the ability to mix and match CUDA and HIP and SYCL code in the same source file, which allows you to create highly optimized code paths for specific devices. Let's assume that you want to create such an optimized code path for some HIPSYCL platform, CUDA or ROCm or even CPU. In this case, you would first check with the HIPSYCL platform macros if you're compiling for your target platform, for example, HIPSYCL platform CUDA or HIPSYCL platform ROCm. If you are, you can define your optimized function. If you're compiling for GPU, this function must be marked as host device, even if it only contains CUDA or HIP device code. Then you can use the SYCL device only macro to check if you're actually in the device compilation path, and if you are, then you can use any arbitrary CUDA or HIP device code, intrinsics, vendor optimized libraries, and so on and so forth. Then inside your regular SYCL kernel, you would again just check if you're compiling for your optimized platform. If you are, you call your optimized function. Otherwise, you call some regular SYCL function, some regular SYCL implementation for portability. We also support a couple of extensions in HIPSYCL. For example, the FP atomics extension allows SYCL atomic class to operate also on floating point types if that's supported by the backend, so CUDA or HIP. And then there's also an experimental extension that can dramatically simplify code that requires the same accessors multiple times in a row by letting the SYCL queue automatically require them. This can really reduce a lot of boilerplate code. And then there's the custom parallel for work item synchronization extension, which allows the user to customize the behavior of this hierarchical parallel for with respect to synchronization. This SYCL specification requires that at the end of a parallel for work item, a barrier must be executed. However, in HIPSYCL, you can pass some template arguments to parallel for work item. For example, if you pass sync none to it, then no synchronization will be done at the end. In the same way, you can also tell it to do a memfence instead of a barrier, for example. If you pass no template argument at all, then it will still do the regular barrier as required by the specification. So to wrap it up, HIPSYCL is an implementation of SYCL for CPUs, NVIDIA GPUs, and AMD GPUs. It provides full interoperability with CUDA or HIP at source code level, and really allows you to create highly optimized device-specific code paths using the latest CUDA or HIP intrinsics, for example. By design, kernel performance can be expected to be on par with regular HIP or CUDA, and if you're interested in learning more about how it works and maybe also seeing some benchmark results, then I recommend you check out my talk SYCL Beyond OpenCL, the architecture, current state, and future direction of HIPSYCL. So go check it out on its GitHub page if you're interested, and if you have any questions, please feel free to drop me an email at any time. Thank you.
Hello, my name is Ronan Keriel, and I work at the Xilinx Research Labs, and I'm currently the editor of the Chronos SYCL standard specification. I'm going to talk to you about TriSYCL, which is an open source C++20 based SYCL implementation. So TriSYCL is one of the current SYCL implementation available. So the SYCL standard started around 2011 as a high-level model for OpenCL inside Chronos. And in 2014, TriSYCL started at AMD, the Performance Application Engineering, try understanding what was SYCL and how we could use it. So since then I moved to Xilinx, and now TriSYCL is mainly backed by Xilinx. The main target for TriSYCL is the CPU first. So it's a pure C++ library providing the SYCL host device that use only C++ classes to emulate hardware features without requiring a real device compiler. But it's a good opportunity also to experiment to new ISO C++ features. And in the SYCL history, so Compute CPP wasn't actually still the strong production implementation, but it is a closed source. So in order to bootstrap the ecosystem, we thought it was good to have an open source implementation to back up the open standard, the SYCL. So in that sense, TriSYCL help the development of the ecosystem and also some other implementation, allowing them for quicker prototyping and try some extensions. So that's why now we have several other implementation. In 2017, we made a prototype to target our Xilinx FPGAs by developing a Clang LLVM-based device compiler for our Xilinx OpenCL stack. Interestingly, Intel announced that they were working on open sourcing their implementation of SYCL, which is the base of their one API DPC++. And since it was quite more robust than our minimalistic TriSYCL device compiler, we decided to merge our effort and to recycle the Clang LLVM device compiler from Intel into our development. But we still reuse our own LLVM passes from TriSYCL. So we participate to the public code review on the upstreaming implementation from Intel. And we also reuse our TriSYCL C++ runtime in our own oncoming implementation of TriSYCL for the Versal ACAP I will describe in another presentation. So TriSYCL, it's an incomplete implementation of SYCL 1.2.1 plus some extension for some deprecated standard version. It's a clean room open source implementation, which is C++ 20 with a header-only templated class. In that way, it's simpler to integrate in existing project. And it's modern C++ because it's make easier to implement and to experiment in an easy way. And it's also it improves the usability for the end user SYCL programmer by giving a language shortcut. And as a side effect, we can also able to give some feedback to ISO C++. So in all this project, we try to fight back the not invented here or not written here syndromes. So we relied on all the libraries available, so relying also on OpenMP, TBB, and StudsThread for efficient CPU execution. We rely a lot of Boost libraries, for example, for the OpenCL interaction. And at the end, this project also was used to help the Kronos group to refine the SYCL standard and also some other standard. But because nowadays language are so complex that it's almost impossible to define them without implementing. So in SYCL, we have an OpenCL interoperability mode. And in TriSYCL, it is implemented with Boost Compute. And the interesting part is that it allows to reuse existing OpenCL C kernel in a nice SYCL way. For example, you do not need to develop all the usual OpenCL host API boilerplate to handle communication and things like that. So the SYCL API provide you basically communication and computation overlap for free. So in that way, this SYCL is just a very nice way to simplify OpenCL programming. And relying or recycling existing OpenCL kernels is also very useful in the FPGA world, where you have existing kernel that can also return in some RTL language, such as Verilog or VHDL, or you can also use some specific C++ extension for FPGAs. And you can recycle these kernels in the OpenCL framework, and then at the end you can use them directly from the SYCL framework in a simpler way. So you can access to a lot of libraries directly optimized from the vendors in that way. Even to access some specific hardware you have on FPGAs, for example, high-speed Ethernet. And that's how at some point we had a TensorFlow SYCL where you were able to execute directly some FPGA kernel from it. So the current architecture of the implementation is that, so you start from an existing SYCL program, and in the simple case where you just want to run this on CPU, you just use your usual host compiler and you just include the SYCL runtime, and then you will just have a normal host executable using, for example, OpenMP or TBB to run in a faster way on CPU. More interesting is that when you want to target a device, then you need the Clang LLVM device compiler from SYCL that will extract, for example, the kernel part of the program, and will generate some LLVM IR with some decoration. That's what we call the SPI de facto. And from that, you can target your OpenCL like device compiler backend that will generate some kernel binaries. And the host part is also compiled by the same kernel device compiler that will do the opposite work just by selecting all the non-kernel parts and add the glue logic to the final binaries to be able to execute some kernels generated by the device compiler for the device. What is the we have a useful extension in very simple one in SYCL, which is that we can have a configurable SYCL namespace, because in some cases it's very useful to combine a different version of SYCL in the same program. So we have the normal #include that when you use it, will declare a SYCL in the normal SYCL namespace. But if you want to have the SYCL implementation aside, then you can use this way to include the headers, and then it will declare everything in SYCL. So that means that it leaves a room free for some other implementation to coexist with SYCL. And for the lazy people, we have this header. When you include it, then you just have to use a SYCL namespace, sparing 4 characters. So if you're interested about SYCL, you can look online for it. The open source version for our Xilinx Versal ACAP is not ready yet, so it will be open sourced later. Stay tuned. So to conclude on SYCL, it's not a product to be used by normal SYCL programmers, in the sense that it's an incomplete implementation, and there are fortunately many other SYCL implementation available today. So it's more like a research project to experiment on future SYCL version, on some extensions, on some new architectures ongoing, and to also experiment on some future C++ versions. But TriCycle has a simple architecture using the latest C++. And this simple architecture allows simpler interacting with some other implementation because at the end, on a real target, you will have to handle with a wide variety of accelerators. So probably you will need collaboration of several SYCL versions to address everything. But since it's a pure C++, then you can build some other abstraction for any kind of devices, and that's what I will present in another presentation. And a nice side effect of pure C++ TriCycle is that you can use a host fallback mode to emulate your target and to debug on the CPU some kind of hardware features and basically co-design on your CPU just for free. And also TriCycle is independent from OpenCL with the concept of various backends. For example, we can target OpenCL. That's what we do when we use our designing the FPGA compiler flow, but we can also use a non-OpenCL flow when we target our Versal ACAP. So to finish, I think that TriCycle contributed to the good open source collaboration we have now across the SYCL community. And so that's why it's important to have open source implementation for open source standard. That's it. If you have some question, you can probably ask them online. Thank you for your time.
Okay, so we're going to move into the Q&A stroke panel part of things. I'm going to attempt to feed in the panel guests, so bear with me just for 1 minute.
Hi, everybody. My name is Michael Wong. I am the chair of SYCL. Welcome to the live Q&A session. I would like to ask each of the panelists to introduce themselves. So I would like to ask each of the panelists to introduce themselves quickly, starting with Renan.
Hello, so I'm Renan Cariel. I work at Xilinx Research Labs on higher level programming models based on C++ for various accelerators such as FPGAs or coarse-grained reconfigurable architectures. And I also involved in SYCL for a while, and I'm currently the spec editor for the SYCL specification from Khronos.
Thank you, Renan. Next is Gordon Brown.
Hi, so my name's Gordon Brown. I work at Codeplay, and I'm the technical lead on the Compute CPU runtime. Also a contributor to the SYCL working group.
Thank you, Gordon. Next is Axel.
Hi, everybody. I'm Axel Alpay. I work for Heidelberg University, and I lead the SYCL project.
Thank you, Axel. Next is James.
Hi, I'm James Broadman. I work at Intel on SYCL and DPC++.
Thank you, James. Next is Michael.
Hi, I'm Michael Steyer. I'm a technical consulting engineer at Intel, focusing on software development tools for HPC.
Thank you, Michael. Next is Igor.
Hi, my name is Igor. I'm a senior technical consulting engineer. I'm supporting compilers at Intel.
Thank you, Igor. And we also have Rod Burns online, who's coordinating everything for us. Thank you, Rod. So this is a great time to jump into the questions about all the different implementations. Probably the first thing I've been watching is the discussion about FPGA. So I'm going to put that right away, front and center. We did have a question yesterday in the live panel about what are the tool chains for FPGA on SYCL. So I'd like to ask the panel to respond to that, because that seems to be a very hot topic at this moment. And there's going to be a couple of follow-on questions about that, actually. So would anyone on the panel like to respond on that?
Okay, so perhaps I can start, since I work more precisely in a company involved in FPGA. So SYCL has a strong advantage to program FPGAs, and because it's a modern framework, and it allows to program the full application in a uniform way, because in SYCL, since it's single source, you can optimize both the host part, which is also important, and the device part, which is essential. And so it provides you some modern way to optimize globally your program, and to write, for example, some generic libraries, so you can have really what is implemented on the FPGAs to be optimized according, for example, the data types used by your libraries. I don't think that today there are some product SYCL implementation for FPGAs, unfortunately. At least at Xilinx, it's only a research project. Because we are also using the upstream device compiler, mainly developed by Intel, and our current HLS and OpenCL toolchain is a little bit back in time, in the sense that we do not internally at Xilinx support the latest version of Clang and LVM, so that's why we have some struggle to follow what Intel is doing on the latest Clang and LVM. But I hope we will get there in the future.
Great. This question actually started with Andre asking if Coplay had any intention of doing something in that direction. Gordon, do you know anything about that? And then I'm going to ask Igor to maybe jump in from an Intel side.
So Compute CPP doesn't currently support any FPGA platforms. We largely target mobile, embedded, and automotive platforms, as well as desktop platforms for the Community Edition. So there's no current plans for FPGAs.
Okay, all right. How about any of the Intel folks? Igor, Michael, and James? So the question was about specific support of FPGA or FPGA tool chains on SYCL to the Intel people.
Yes. FPGAs are a supported platform with our DPC++ compiler, and it works with, I think, a few of the FPGA models we have today. And FPGAs are a bit of a different type of device, so in order to get the best performance, you might have to structure your program in a different way than you might for a CPU or a GPU. But it is pretty nice that you can have a single tool chain that can work across multiple different types of platforms. And this is possible because of using things like SPIR-V and higher level models like SYCL.
Right. In fact, I think this is one of the central tenet of one API. Is it not?
Across.
Yeah. Thank you. Okay, we're going to come back to FPGA, but I want to follow in the order of questions that's on Slack. Once again, if you have questions, please start posting them on Slack, on the Slack channel under Discuss SYCL Tutorials. The second question, while I have the Intel folks on, is about the current status of DPC++. Now, I know that Igor has already posted the link about the status page, but maybe if you guys can say something about, what are the latest, what are the features that are working? I think a lot is, so I think a lot of people would want to know the answer to that, and that would give them a good feeling about where Clang LLVM DPC++ is going, and how long it might be before everything is complete. I know that's probably would be a guess.
Sorry, are you talking about the effort to upstream our open source compiler into mainline Clang and LLVM?
I am, yes. Mm-hmm.
Yes. So this is ongoing. It's not going as fast as anyone would like, but such is the speed of large open source projects. We have a couple links that I think Igor posted in the Slack channel that have status of various different patches and features we're trying to upstream into it. But this is going to be realistically a multi-year effort. But as we do it, and if people also want to help us do this, at the end of the day, then we'll have SYCL be a first-class language in Clang and LLVM.
Excellent, thank you. Well, I think I think people should be aware that these kinds of things takes a long time, and the more people that have helping it, the better. And now I think this project definitely is gathering momentum in terms of having multiple companies directing their effort on top. You heard Renan saying that he's redirecting his tricycle effort to integrate with the Clang LLVM upstream effort. So you see that, and certainly from Gordon's presentation, he pointed out, no, I think it was from Igor's presentation, he pointed out that CodePlay contributed the NVIDIA support in there. So you can see that multiple companies are definitely heading in that direction. Anyone else would like to add anything on the current upstream effort? Okay. Well, let's go back to SYCL because Andre keeps asking these excellent questions. And I know that some of them have been answered, but it bears that everyone can kind of hear whatever people's reactions are. So Andre asked that SYCL provides the same means of spatial partitioning of local and global memories on FPGAs by pragmas, the same performance as in OpenCL or HLSC cannot be achieved. Alternatively, it would be very good to implement the specific per each FPGA technology memory partitioning by the optimizer. But at present, we only have pragmas. So I think, Renan, you had some replies about that. You want to discuss this a little bit more?
Can I actually jump in here first?
Oh, yeah, absolutely. Go ahead, James. Yeah.
So I think really this is at its heart a question about device-specific extension support in SYCL.
Right.
For specific types of hardware features or widgets that exist in one type of device, but not necessarily others. And that is an ongoing problem. We're looking to define a more fully fleshed out extension mechanism going forward, which I think should make it easier to add support, more device specific support as kind of first class C++ objects for these different types of hardware features, rather than the kind of pragma based approach that is easy to get working in a tool chain first, but isn't necessarily the right or beautiful C++ way to do things. And I think Ronan probably has some things to add on that front.
Yeah, I'm really glad you pointed that out, that difference between C++ view about pragma. So, Renan, you want to add your?
Yeah, I think, yeah, if we can find some pure C++ way to express extension, it will provide a seamless integration in some existing programming flows. And it has also some advantages compared to some attributes or pragmas kind of alien syntax, is that you can use this, for example, the C++ classes to provide some co-design approaches, because you can have some device emulation or something like that when you run your SYCL program on CPU, and then it's very, very useful to experiment with some kind of pseudo architectural details on your CPU, just to debug and then and develop your program with normal toolchain. So that's great if it's just pure C++.
Okay. We are getting down in time, so I am going to have to jump through quickly to a last question. Let's see. Michael Buchner asks, is it possible to use HIPSYCL to create object code for device code and possibly boilerplate code required to run the device code and use another compiler, possibly proprietary such as MSVC, to create object code for host-only code with both object code being linked into a single application? This sounds like getting a lot of ABI compatibility issues, but I'm not an expert in the area. I figure I jumped to this question because we haven't had Axel jump in yet. Go ahead, Axel.
Yeah, so so HIPSYCL is based on Clang, the Clang CUDA or HIP support with an additional plugin to add support for SYCL constructs. And CUDA in Clang really works as an integrated compiler. So you have Clang compile both the host part and the device part of your program. This is different from other SYCL implementations, such as, for example, Compute CPP, where you can tell Compute CPP to really use an arbitrary host compiler for the host portion. This is not easily possible with HIPSYCL. You could, of course, tell it to, you can tell HIPSYCL to emit the device code, as LLVM or PTX or whatever, and then inject this with another compiler into CUDA, for example, but this will be painful. Or, of course, what will be possible is if you have different compilation units in your program and only some of those use SYCL code, then you could compile those with the HIPSYCL compiler and the other compilation units with some other compiler, assuming that they are ABI compatible, as you point out. Since you specifically mentioned MSVC, HIPSYCL does not support Windows yet, so MSVC will probably be out of the question.
Okay, thank you. Anyone else would like to add to that question, answer that question? We are coming up on the hour, so we would like to switch to the stream. I do still have Andrei Olenikov's question, and I'm going to keep that in the bank and ask it at the next Q&A, if that's okay, Andrei. But thank you for your question. Everyone, please feel free to keep updating the question banks. Rod, would you like to take back control and restart the stream for the next part now? Track.
Yeah, thanks, Michael. I'll start the next set of presentations now.
Now, we are going to talk about Intel DPC++ compatibility tool. We will talk on what is Intel DPC++ compatibility tool, learn a migration flow for a simple single file and more complex project migration. Also take a look on some advanced tool options you may use. Intel DPC++ compatibility tool, further we will use compatibility tool or DPCT as a name, is a part of Intel One API-based toolkit, a core set of tools and libraries for building and deploying high-performance, data-centric applications across diverse architectures. The tool assists in the migration of a developer's program that is written in CUDA to a program written in data parallel C++ or DPC++, which is based on modern C++ and incorporates portable industry standards such as SYCL. Note that the beta release of compatibility tool is available at this moment. I want to highlight that the idea of migration process is that you need to do it once and then maintain a migrated DPC++ code, so there is no need in iterative process. Other important note is that we expect the tool to migrate approximately 80 to 90% of the code. Of course, it depends on the code and will be different depending on workload, but average ratio is expected to be around 80 to 90%. This means that the compatibility tool may significantly minimize the code migration time. It is available on both Windows and Linux and also supports an integration to well-known IDEs such as Visual Studio and Eclipse. DPC++ compatibility tool is not available as a standalone downloadable installation package and is not open source, so you need to install a OneAPI-based toolkit to get it. Set the environment for the tool using following commands after the installation of the tool. You can set the environment for all tools from base toolkit using a setvar script. The general invocation syntax from the operating system shell is a command dpct with optional arguments and source files. You can get the list of the Intel DP++ compatibility tool specific options by passing the option --help. We will talk about some interesting options later. To see the list of the language parser options, pass -help option using the following syntax. Note that in some cases you will need to change parser options, for example, to change the default C++ standard version. This is a usual dpct usage workflow. As an input to the tool, you need to pass the sources of CUDA application. Options, macro definitions, etc. that can be gathered via a special tool called intercept build. In a simple case, we don't need to collect settings from makefile and may skip it. You also need to provide relevant CUDA header files, which can be done via an additional tool option. The compatibility tool will attempt to migrate the sources. It is important to pass all required build options, headers and macroses to the tool, so that it could parse the source code correctly. In cases when the tool doesn't support migration of some features, it inserts comments with additional insights into the generated source files, and also generates warning in the tool command line output, so further code migration should be done by the developer. Note that the migrated code is a DPC++ code, but it also has helper functions, which are coming from the compatibility tool. You should add the include path to dpct header files for the compilation of the migrated code. When additional efforts are required to complete the migration, the tool produces a corresponding warning and also adds comments into the code. Use grep in the generated source files for dpct10 to find comments inserted by the tool. Warnings may look like this. Then you may find a clear description of the detected issue in the documentation and get an actionable suggestion. At this moment, there are 35 different warnings generated by the tool. Now, let's take a look on how a basic invocation of the tool usually looks like. By basic, we mean a simple one-file migration where we don't need to care about additional options like makefiles and compilation databases. We will cover this later. To migrate applications, the tool requires certain CUDA header files, which are not provided with the tool. You can make them available by pointing to them with the CUDA include path option in the command line. If this option is not specified, then the compatibility tool looks for the CUDA header files in some default paths. Currently, the tool supports the migration of programs implemented with CUDA versions listed on the slide. The list of supported languages and versions may be extended in the future. As I mentioned earlier, sometimes you need to change parser options, for example, to set a default C++ standard. You can do it via extra arg option. For instance, invoke the following command to migrate single source file with C++11 features. This is an example of a simple vector addition code migration to DPC++ by using a compatibility tool version beta 05 shipped with one API-based toolkit. Note that SYCL and dpct header files are included in the migrated code. Vector add kernel is migrated to a corresponding DPC++ kernel, where SYCL item class is used to identify work items' local IDs. For memory allocation and deallocation, the Unified Shared Memory APIs are used. For instance, malloc device and free functions are used in this sample. A kernel call migrated via helper function getDefaultQWait call from dpct namespace. It is a static function to get the default queue and wait till all the tasks in the queue are done. Then we are submitting a command group and invoke a parallel for to enqueue a kernel as a parallel execution over the ND range. Since a getDefaultQWait function explicitly calls wait to complete all tasks in the queue, the call to memcopy is generated after the submissions of the command group, so we are sure that the data is updated and we may copy it to a host. We may finally deallocate the memory via free functions. If your project uses make or CMake tools, you can utilize compilation database support to provide compilation options, settings, macro definitions, and include paths to the DPC++ compatibility tool. The compilations database is a JSON file containing the commands required to build a particular project. Compilations database can be generated by running the intercept build script, which is provided as part of a compatibility tool. The tool parses the compilation database and applies the necessary options when migrating the input sources. To create the compilation database, you need to configure your project and make sure it is cleaned. Then, invoke the build command, prepending it with intercept build. The intercept build script runs your project's build command without building the original program. It also records all the compiler invocations and stores the names of the input files and the compiler options in the compilation database file. By default, the Intel DPC++ compatibility tool looks for the compile command.json file in the current directory and uses the compiler options from it for each input file. The location of compilation database file can be changed using the "-p" option. The following steps are similar to what we already shown with a single file migration. Please take a look on the usage workflow overview. There is a nice real code example there, and you can try to pass all migration steps, including compilation database file creation. I also want to show some interesting compatibility tool options you may use in order to control the code migration process. Some DPC++ extensions are helping to simplify the code. By default, the compatibility tool generates the code with disabled class template argument deduction. In case it is enabled via a specified option, the migrated code will use a C++17 style with no template argument for some SYCL types. Since the generated code is using C++17 features, to compile such code you would need the compiler with C++17 support enabled. One more extension helping with code simplifications is unnamed kernel lambda. SYCL allows device kernels to be defined in a variety of ways, one of which is as a lambda. SYCL 1.2.1 requires that a kernel name be specified as a template parameter. DPC++ has an extension which makes naming of lambdas at invocation time optional. By default, the tool generates a code with unnamed kernel lambdas in the code. You may set the option SYCL named lambda to generate the code with named lambdas, which is in accordance with the existing SYCL standard. This is the last option I want to show in scope of this presentation, which is on in the compatibility tool by default. The namespace generated by the tool is SYCL and not SYCL. The option No CL namespace inline will force the tool to use a full namespace. Note that there are other interesting options available in the tool you may use in order to control the code migration. Thank you for your attention, and now we are open for Q&A session.
Hello, my name is Michael Steyer. I'm a technical consulting engineer within the Intel Architecture, Graphics and Software Group. And today I want to talk about the Intel Offload Advisor, which is part of our OneAPI developer toolkits. So let's start by looking into what the Advisor tool actually is. And some of you might already know it from the past, from our Parallel Studio packages. It's a tool that gives you certain advices on what to do with your application in order to get more performance. So historically, it all started with the threading advisor, where the advisor would analyze your application, which is serial and not parallel, and therefore identify good candidates for parallel regions. And in addition to that, also model the speed up you would get by parallelizing these regions with multi-threading. Later on, we had the vectorization advisor, which follows a similar approach, but instead of looking into thread parallelism, that was looking into data parallelism. And the background is that in modern microprocessors, we have quite large vector capabilities, and we noticed that not all people are leveraging those capabilities with their applications, and therefore losing a lot or leaving a lot of performance on the table. And the advisor now allows you to analyze your application and tell you for the different code regions, especially loops here, which parts are vectorized and which parts are not vectorized. So vectorization is something that can implicitly be done by the compiler. However, on most scenarios or real-world codes, it often happens that the compiler is not certain about dependencies in between different loop iterations, and therefore has to assume worst cases and will not vectorize those loops. And therefore, you will have to manually tell the compiler via explicit pragmas, for example, that there are no dependencies in between loops. And this is the whole process that the advisor guides you through. So it tells you which loops are not vectorized, what is blocking vectorization, what is the compiler report attached to a specific loop, and then it tells you what would be the next steps. For example, like I just mentioned, adding a pragma in order to tell the compiler there are no dependencies. But also it looks into those loops which are already vectorized and tells you what the efficiency of these is and how you could potentially improve this efficiency even further. So for those of you who are familiar with the Berkeley roofline model, which helps you to tell what is the maximum performance your application could achieve on a given architecture, we have an implementation which is a little bit more sophisticated, the so-called cache-aware roofline model. That is what you see on the bottom right. And historically, people have done these roofline models with pen and paper and had to calculate the number of floating point operations as well as memory accesses of a certain loop or application. But the advisor can do this automatically. It also draws you practical roofs. That means it runs micro benchmarks in order to see what real performance your given architecture can provide in terms of memory bandwidth and floating point operations. And now, most recently, with the offload advisor, we have a third component, which is now a capability of the advisor to analyze your host or CPU application in order to find interesting regions for offloading to an accelerator like a GPU. Interesting in terms of promising performance, speed up you could get by offloading. So as you can see, the advisor tool really is a tool that gives you advice and guides you through the whole process of parallelizing vectorizing, or offloading an application. So what specifically can the offload advisor tell you about your code? First of all, it can model the performance on the accelerator and therefore give you an idea what would be the speed up by offloading your code. Here on this particular example, it's an integrated graphics Gen 9 architecture. And you would see here that the accelerated part would be a small fraction only of the original application runtime. So obviously this application would be a good candidate for offloading. It will also tell you which regions of your code would be good candidates for offloading, also the particular speed up for that region. And in addition to that, it's showing you what is limiting the performance on the accelerator, right? So in this case here, it is the cache bandwidth that is actually limiting the offload performance. And also it will tell you what other code regions were not good candidates for offloading and for what particular reason they were not good candidates for offloading. Here, for example, if it's not profitable because it's running for such a short time that the offload overhead would be much higher than the gain you would get. So here you see the resulting HTML file of the offload advisor for the specific application, and similar as on the slide before, you already see we are on the summary page here and you see the general performance matrix of your application. You see what's the bounding the offload, what is the overall speed up you get, what regions have been or can be offloaded or good candidates for offloading versus those that are not good candidates. You also see here the specific configuration of the accelerator, which is a GT2 integrated graphics in this case. And on the top you would see there are also different tabs where you can go into more details of which regions are offload regions, and you would see which code parts, you will see your source code, would be offloaded and what is the particular speed up for each region, as well as additional configurations and log files. So on this slide you can see the second tab from the offload advisor, summary report HTML file, where it shows you more details with regards to your offloaded region or regions that were considered for offloading. It shows you the time of those regions. It shows you the floating point operations as well as the memory access or memory bandwidth of those regions. And it also shows you the overhead, here referred as tags, by involving those offload regions, by copying memory back and forth in between host and accelerator and so on. And these are then basically the regions where you would go ahead and offload those to an accelerator by, for example, using data-powered C++ or using OpenMP offload pragmas. So now we want to have a brief look into how the offload advisor actually works under the hood. And first of all, it is important to mention that this is not a SYCL accurate system simulator, because such an accurate system simulator would make it far too complex and would have too large overheads in order to make it applicable for user-specific codes in order to do some forecasting of speed ups on an accelerator. So therefore we rather look into some modeling of the performance on an accelerator, where we take into account the compute throughput model, which looks at the floating point operations, the memory subsystem model, which looks into the memory hierarchy and subsystem, and then also the overhead, which we look into, where we consider the data transfer in between host and accelerator, as well as the overhead that comes into play by invoking the kernels on the accelerator. So given that we have a host or CPU application with two regions, region X and region Y, we run this code with the advisor on the host, and via dynamic instrumentation we count the number of operations, so in terms of instructions on the host, and then we model these instructions on the device, looking into the specific latencies for all of these instructions on the accelerator. And then we have a certain amount of time that is needed to do the computational part on the accelerator. In addition, we also look into the memory operations looking at the whole memory subsystem on the accelerator, and we also model these instructions there and the latencies involved. And now we assume that you can overlap computation as well as memory access, and therefore we just look at the one which takes most of the time, and then we add our overhead in terms of offloading as well as kernel invocation time to that. And here, as part of Advisor, that is referred as tags. So in summary, each region time would be computed by the maximum of either compute or memory plus our overhead, which consists of data transfer and kernel invocation. Now that we have this, we can model the overall time for each individual region or kernel, so to say, and then we know if it's profitable to offload that region to an accelerator or not. And based on this, you will see how Advisor then models the overall performance of your application. On this slide, we are talking about things to pre-consider when you want to use the offload Advisor. So first of all, and important is that you compile your application with symbols. So here with this -G flag, which adds the source code symbols to your binary, and therefore you will have references to source code regions. Otherwise you would just see memory addresses of your functions without having a name, and therefore the symbols make the whole thing very practical for you in order to refer back to your source code regions. Also, please mind to use an optimization flag. O2, as I mentioned here, would actually be default for our compiler. However, since we are having the same behavior as with the GCC compiler, per default, if you add the flag -G for symbols, it would fall back to 0, so without optimization, because it assumes that you're running a debug build. So make sure you have the symbols as well as an appropriate optimization level specified for the compiler, and then you can get started with your build. If you're using a higher optimization level like O3, please also add the no IPO flag here. This is Intel compiler specific in order to disable specific optimization that might make it hard for Advisor to analyze your code regions. Your application is compiled and ready. You will have to source the environment variables of the Advisor tool, depending on how your system setup looks like. Possibly it is also a part of the module system that is being prepared by your system administrator, but nevertheless we recommend sourcing the Advisor environment variables that are part of the installation directory, and that puts all necessary libraries and binaries in the path of your system so that you can start using the Advisor right away. And please mind, this offload Advisor is only available on Linux. Now that you have your binary compiled as well as the Advisor in your environment, you can go ahead and directly run the full offload Advisor analysis with a single script that gives you less flexibility than doing the individual steps independently. However, is the easiest to get started approach, and therefore you could run this Advisor XE -Python binary, use the Python script from the offload Advisor that APM environment variable is set after sourcing the Advisor. You can directly use this command line like here. Then you specify a project directory where you want your results in, and then you can either specify additional options, for example, like the GPU type you want to model, or you can directly specify your application after a double dash that basically separates the command line parameters of the Advisor tool from the command line parameters of your application for the interpreter. And then the run OA Python script, which is part of Advisor, marks up all regions that are profitable for analysis and goes into, or for offloading, and then goes into deeper analysis with those. Again, if you go into the individual collection steps, instead of using this one script that does everything, you can select and filter a little bit more on the individual regions. And after the whole thing has been collected, you have your report HTML file in the perf models nm with a number subdirectory. And this last slide is just to summarize that this run offload advisor Python script actually does a lot of steps and simplifies the whole thing. But if you want to have more freedom and control, you can use the individual steps to go through that. And you see there's first of all, a survey report that gets a summary of the whole application run and times of individual functions. Based on these functions taking most of the time, it does a markup and then goes into the instrumentation and traffic simulation of the cache subsystem or memory subsystem in general, and then also counts the floating point operations and so on. And as a final step, then does the actual performance modeling for your specific architecture. And that's it so far for the offload advisor. If you have any questions, please feel free to use the chat. Thank you.
Hello everyone, thank you very much for listening to this talk. My name is Gordon Brown and I'm going to be giving a brief presentation on some of the work that we've been doing at CodePlay to bring support for NVIDIA GPUs to SYCL. Now this talk is a reduced version of a talk by my colleague Roman Reyes that's going to be in the main IWOCL SYCLcon track, so credit to him for much of the materials in this. So SYCL applications can now run on NVIDIA GPUs with a native CUDA backend using DP++. That's Data Parallel C++, the open source SYCL implementation led by Intel. This means that any SYCL application can now run on NVIDIA GPUs as well as the range of existing devices which could already support SYCL. This is because the CUDA backend is plugged into an existing SYCL runtime, so it uses the same standard SYCL API. So in this talk, I'm going to cover a few topics. First, I'm going to give a high-level overview of how we added a CUDA backend to DP++, which is now available upstream within the DP++ project. Next, I'm going to cover some of the experience we gained in porting SYCL for a non-OpenCL backend, and take a look at some of the proposals that we have made to the SYCL working group for SYCL 2020 as a result. Finally, I'm going to show you how to use NVIDIA support in your SYCL applications. However, a quick disclaimer before I begin. Firstly, NVIDIA, the NVIDIA logo, and CUDA are trademarks and are registered trademarks of NVIDIA Corporation in the US and or other countries. And also, CodePlay is not associated with NVIDIA for this work, and it is purely using public documentation and widely available code. So first, I'm going to show you how we added a CUDA backend to DP++. So going back, SYCL was first designed for OpenCL 1.2. And if SYCL 2.2 had been fully ratified, it would have targeted OpenCL 2.2. However, some existing SYCL implementations were already starting to support non-OpenCL backends such as ROCm or OpenMP. So we had an open discussion about what other backends SYCL could be a high-level programming model for. One option for this was Vulkan. Now this is possible, but it's not so straightforward, because SYCL was not designed for graphics. There is also a potential path already for Vulkan via CLSPV and CLVK. So what about CUDA? Support for NVIDIA GPUs in SYCL was probably one of the most requested features we got from SYCL applications developers. We had existing experimental support for NVIDIA GPUs via OpenCL and PTX, but this was not ideal. Native CUDA support would be a much better fit for the SYCL ecosystem. DP++ is an open source SYCL implementation led by Intel. The long-term goal is to merge it into upstream Clang and LLVM. DP++ has various extensions to the standard SYCL 1.2.1 API, and also provides a plugin interface referred to as PI, which allows it to support additional backends to the existing OpenCL backend. This is where we added support for NVIDIA GPUs via CUDA. As you can see here in the diagram, all backends use the same DP++ runtime, which calls down into PI. So we added a new backend here for CUDA, which will take the PI calls and direct them down to the CUDA driver API, which ultimately enqueues work to the NVIDIA GPUs. Now there are a lot of similarities between SYCL and CUDA, so there are many places where this mapping was fairly straightforward. However, there are some places in which this was more complicated. I'm not going to go into the details of this too much. However, if you're interested, please check out my colleague Roman's talk in the main IWOCL SYCLcon track called Bringing Performance Support for NVIDIA Hardware to SYCL. Here we can see some preliminary performance results from a local build. For this we are using Babelstream 3.4, the current tip, and CUDA 10.1 with a GeForce GTX 980. The bands here represent bandwidth, so higher is better. The orange is the DP++ CUDA backend, the green is plain CUDA, and the light blue is OpenCL stream running on CUDA. As you can see, there is still a slight performance gap compared to native CUDA, but the difference for everything except for DOT is less than 10%. But note that this is still early work. Now here we see the results of the DP++ CUDA backend with an internal development branch, which has a different implementation for event handling. This is shown here in yellow. Performance now in all cases, including DOT, is much closer to native CUDA. Now this is still in development, but we hope to see this reach tip along with a number of other performance improvements soon. Now I'm going to go over our experiences of porting SYCL to support a CUDA backend, what we learned from this, and what we proposed for future versions of the SYCL specification. So as SYCL was originally designed for OpenCL, not everything was going to map to CUDA perfectly. So what worked and what didn't? Firstly, much of SYCL worked very well and was able to be mapped to run on top of CUDA, including the SYCL platform model and memory model. So what didn't work so well? After introducing a new backend, there was no way to differentiate between platforms from different backends. Interoperability also wouldn't work, as it required OpenCL types. SYCL 1.2.1 images couldn't be supported as is because CUDA cannot support dynamically sampleable images, like OpenCL can. So in CUDA you have to specify the sampler when you create the image if you want to use one. Finally, the program class was tied too closely to the OpenCL compilation model. From this experience, we proposed a number of new features for SYCL 2020 to try to tweak the API to allow CUDA to be a fully supported backend, but while not deviating from what made SYCL what it is. The first of these was the SYCL generalization. What this means is generalizing SYCL to be able to support non-OpenCL backends. Now the execution, memory, and platform models would remain the same, and the API would be largely unaffected by this. But the platform model would be extended to be capable of supporting multiple backends and not just OpenCL. Next up, there are SYCL modules, not to be confused with C++20 modules. Modules are a replacement for the SYCL 1.2.1 program class. A module represents all the kernel functions in a translation unit, and they can also contain multiple file formats, such as SPEAR, SPEAR-V, PTX, or even a vendor-specific instruction set. The interface is now also type-safe and thread-safe. A few other proposals I'd like to cover quickly. Generalization of interoperability to support different backends rather than just OpenCL. A refactoring of images to replace the current SYCL 1.2.1 image class with the two sampled image and unsampled image classes. And finally, the host task, which allows for native C++ functions to be scheduled by the SYCL runtime using the existing SYCL memory model. Now, unfortunately, I don't have time to go into all of these in more detail. However, if you are interested, I am presenting a talk in the main IWOCL SYCLcon track called SYCL 2020 More Than Meets the Eye, which will cover the generalization, modules, and host tasks in a bit more detail. Now lastly, I'm going to show you how to use NVIDIA support in DP++ for your SYCL applications. So the first thing to do is to download or build a DP++ package. There are daily builds as well as more stable monthly builds available at the link here. And there are also detailed instructions for getting started. Once you have DP++ installed, you can compile with the DP++ compiler as normal, but using the CUDA triple NVPTX64-NVIDIA-CUDA-SYCL device, as shown here. Then, once it's compiled, you just need to enable the CUDA backend in the SYCL runtime by setting the environment variable SYCL_VE to PI_CUDA, as shown in the example here. And that's it. It's as simple as that. One thing to note though, make sure that your SYCL application is using an appropriate device selector so that it'll choose an NVIDIA device. Also, using both the OpenCL backend and the CUDA backend at the same time is not yet supported. Okay, thank you very much for listening. We should now have some time for questions.
Okay, so we're going to move back to the panel now. I will switch over to Michael.
Okay, thanks everybody for coming back. We are into our second Q&A session regarding the talks from previously, but we also still have some questions from the previous Q&A. So I'm going to start with that from Andre. He asked, will my source be paused twice during compilation, once for device and once for host pod? And could the host compiler use information about device code for optimization? The implementers on the panel, what do you guys think of that question?
So maybe I will start.
Go ahead, Axel.
So in general, the answer is yes. Your source code will have to be parsed several times, and there's a simple reason. There are macros that lets you check if you are in the device compilation path or in the host compilation path. For example, the SYCL spec defines SYCL device only if you're compiling for device. And this means that if you have some ifdef SYCL device only, your device code can look arbitrarily different than your host your code on the host side. And this means that in general, your source code will have to be parsed several times. Whether this could be optimized somehow, I don't know, but I imagine it would be difficult.
Right, thank you. Who else? Gordon, would you like to say something too?
Yeah, I think I covered it pretty well. But the only thing I would add is that the single source compilation in SYCL means that every SYCL application, when compiled, will have to go through both a host and a device phase. But exactly how that's done is implementation defined. So there is, within the constraints of checking for device compilation, checking for host compilation, a compiler is free to optimize that as it likes. So if you have the separate compiler option, then if you're having something like an integration file, then that can have metadata, which is then fed into the host compilation to kind of infer things. Or if you have a single compiler, it can share information between the host and device potentially. So, but it's implementation defined how that's done.
Okay, thank you. Anyone else would like to add to that answer?
Yeah, I think, this single source approach where you can have this cross device host global optimization is really the strength of single source on page. And then what is interesting is right now we have the same discussion in the MLIR community, and previously in the weekly meetings there was some presentation in that direction. So I think, it's really a good optimization opportunity, which is really fashionable nowadays. So that's a good point.
All right, thank you. Anyone else would like to add to that? If not, I'm going to move on to the next question. There are already a lot of answers there from Joachim Meyer. What offload devices can be selected in the advisor? This is the Intel advisor, to compare with FPGAs, NVIDIA GPUs as supported by the DPC++ compiler. Igor and Michael Steyer, you guys have already answered. Maybe you guys can summarize the answers for the audience, and then others can chime in. Go ahead, Michael.
So in general, we support right now our integrated graphics Gen 9 and Gen 11. Obviously, there will be more GPUs as our products will hit the market. Anyway, there is some freedom in the product that you can define your own GPU with certain parameters and then just model the application again for that given GPU, and that would work. Having that said, there is no FPGA support as of now, and I'm not aware of any plans close by. So right now the focus is really on GPUs.
Okay. Thank you, Michael. Anyone else like to add to that answer? Okay. So actually, actually, let me keep going there because there is another question that is directed towards HIPSYCL. Philip asked, with CUDA support being wired into DPC++ already, how complicated would it be to do the same for AMD ROCm using HIP interface, considering HIP is very close to CUDA?
So I'm not familiar with the internals of DPC++, but HIP is mostly the counterpart to the CUDA runtime API. There's also the lower level CUDA driver API, which allows you to do stuff like manually managing your device code and so on. And this is, I assume, what DPC++ actually uses and not the higher level CUDA runtime. There are also some parts of the CUDA driver API in HIP, but it's not as complete as the runtime API. So I assume that for ROCm support in DPC++, it would be more difficult than porting a, say, CUDA runtime program to HIP. But maybe the DPC++ people can expand on that.
Okay. Anyone like to expand on that? Go ahead, James.
Sure. I mean, if I oversimplify things to some extent, the CUDA backend, I think, provides a roadmap on what sort of changes would be required to make this happen. And I think there's two components. There's wiring up the appropriate runtime routines, which I think is actually should be pretty straightforward to define a AMD plugin for the DPC++ compiler. The other thing that would need to happen would be to change how the kernel code gets compiled. In the OpenCL and Level 0 backends, we use SPIR-V. CUDA uses PTX. AMD would probably need to go to HSAIL or whatever the appropriate backend is there.
GCN or yeah.
Yeah. So we'll happily review and merge that pull request when someone submits it. Wonderful.
Okay, continuing on. We do have a question from Andre. He opined that we have not seen clusters of silicon devices such as GPUs, CPUs, and FPGAs mentioned at IWOCL. At least thinking about supporting cluster compute is important for USM as well as another method of data sharing by pipes. So we might be jumping a little bit ahead to the USM discussion, but discussions about clusters of silicon devices. Anyone would like to jump in? Go ahead, Renan.
I'm not sure what is behind this kind of silicon devices, but otherwise, the Celerity project is an interesting one based on SYCL. I don't know if there are some people presenting it at IWOCL SYCLcon.
Oh, there's also Celerity, right? They are specializing on clusters.
Yeah, Celerity. That's what.
Yeah, that's right. So I also have a question about the Intel One API toolkit.
Can I just add on to that?
Oh yes, go ahead, James. Go ahead, please.
And I'll just give the vanilla answer that MPI and SYCL work very well together. Additionally, there's also a lot of interesting papers coming out these days about combining GPU programming models with PGAS style languages, and so that's I think a path people are starting to look into.
Right.
Yeah, that's a good point. Yeah, I think that the goal of SYCL is not to solve all the problem on Earth, but at least to enable just the minimal stuff to allow other technology to work with SYCL and heterogeneous computing.
Yeah, Yeah, we're not here to solve all the problems. So, James, when you mentioned that, is it direction towards UPC++ or something like that for PCAS?
I don't know if there's any specific direction, but there have been papers from NVIDIA, papers from AMD.
Okay.
It's clearly an area where people are looking, and it seems like it's a pretty good model for the types of systems you're seeing, where you have many accelerators in one box that might want to communicate with each other, and then you might have several of those network together.
Okay. Very good.
And one thing I'd quickly add there as well, that one of the proposed features that we're looking at for later revision of SYCL is the introduction of host tasks and host tasks with interoperability. And this is one way that you can use the scheduling and dependency analysis of SYCL and integrate existing libraries or other programming models.
Exactly. You could use that to elegantly merge your communication inside your SYCL execution graphs. As well, the USM proposal provides features that are useful for implementers of things like MPI to enable very efficient data movement between your devices and your network cards.
Excellent point. Host tasks with interoperability, yes. So there is a question from the discussed presentation side that we got from Robert Schneider about USM. I don't know if you want to answer it here now or wait until after the presentation that's coming up right after this Q&A. He asked, for me, one of the most important improvements to SYCL is the unified shared memory extension. This makes working for complex real-world cases with lots of buffers so much simpler, especially since you no longer have to create all those accessors up front. However, in my opinion, a similar extension should be created for images or textures. Currently, for complex cases with lots of textures, it is, in my opinion, a heavy burden to create all those image accessors up front. I don't know if you guys want to answer that now or wait until after the presentation, or maybe the presentation answers that. Go ahead.
The short answer here is yes, absolutely. That would be a great feature to put in the next version of SYCL after SYCL 2020.
Okay.
Yeah, and we already had this discussion with Robert on that, and so corresponding feature requests are in place for DPC++, so we are working on it.
Oh, very good.
Yeah.
Okay. Rod, I don't know how many more minutes. I have a few more questions I can put up, but I suspect we're getting close to the switch time. Let me know. On the Intel One API toolkit, does it also allow you to build the advisor, the Intel advisor? Does it also allow you to build heterogeneous algorithms? This is actually my question, really. Michael, go ahead, please.
So I'm not sure what you mean by build heterogeneous algorithms. So the idea is you come with a non-offload application, so a homogeneous application, and it would suggest you what would be the benefit of leveraging an accelerator or GPU specifically, and that would then be a heterogeneous application. Well, once you have it at that stage, there's also photo support in the tools. So we have analysis tools for GPU applications, as well as the advisor, for example, can generate a roofline report with your application on a given GPU. So there is support for that as well.
Okay. But what I mean is that it would build heterogeneous computational graphs and then decide which kernels will benefit from offloading to GPUs.
So it does such graphs, such functional graphs for your application, and then mark those regions or those subtrees which are interesting for offloading. Yes.
Yeah, but the final decision is expected to be done by the developer. So it just only show you a tree so you can see your whole application with the calls of the loops and so on.
Okay.
Finally, you can decide.
I think that's what I want. Make sure it shows me the tree. Yeah.
Yeah. It's possible.
Okay. I think that's so far some of the questions, all the questions I have. Rod, are we ready? Okay, so we want to break on the hour. So there's about 4 minutes left to the discussion. So I'm going to go back and ask some of the questions, some more questions about SYCL and FB and FPGAs and all of those things. I think one of the things that I've always that I have the top question. I'm from previous BOFs like at supercomputing. The very top question was, what are some Intel extensions in DPC++, and will they enter SYCL? Now, I know you talked about some of that in your presentation, so this would be an interesting time to review what are some of those some of those top extensions and how you feel about having. In fact, I think some of them have already entered SYCL. So, somebody like to talk to that question? So the question again is, what are some of the Intel extensions that are in DPC++, and how will they enter SYCL? Go ahead, James.
Sure. I mean, most of the extensions that we've come up with for DPC++, we would love for them to appear in future versions of the SYCL standard. Some of them might be a little too device specific, so they may not be, but a lot of the ones we publish specifications for, we think are generally useful features that, of course, we will try to encourage adoption into future versions of the standard. I'll just call out one specifically, and that's USM, which I think has been mentioned a little bit and will be mentioned a little bit more. I think that's going to be a really useful feature in future versions of SYCL.
Okay.
Yeah. SYCL is a democratic standard, and if some extensions are good, they will end up into the standard.
Okay.
Yeah, we yesterday also talked about on day one on Monday we talked about in order queues, right? And some attendees found it useful. So it's also an existing extension in DPC++, and it will be also nice to have this in the SYCL standard finally. So there are actually many of them available, and you can find it on our GitHub page.
Okay.
And yes, we definitely work on getting this to the SYCL standard.
Okay. Okay. Let's continue on to another top question from the question bank from previous BOFs and other engagements. The next question, of course, is, can SYCL run on NVIDIA devices? I think we already have a lot of answers to that. And I don't think we need to add any more unless people want to jump in. The third top question here is, where is SYCL documentation? Will it be as detailed, comprehensive as, say, CUDA documentation? Okay. Go ahead, Jake.
Excellent question. And this is something that I think everyone here involved is working on improving. We already have, many good resources for SYCL out there. There's the SYCL.tech website. There's the SYCL Academy training. Intel's also been producing lots of training material. And as part of this, I think we're all going to work to having better documentation, tutorials, sample codes, and API references for common SYCL classes available going forward. I can't give concrete dates for all of these things, but I think we all know where we want to be, and we're not there today yet.
Right. And this is actually an indication of the first step towards integrating tutorials, having multi-companies participating. We've been on multiple calls trying to coordinate that, and this is one of the first results. And so far, I think it's worked out pretty good. Axel, you want to say something as well?
Yeah, I would just like to add that I agree with all of this, but I'd still like to add that people shouldn't be shy to look into the specification, because the SYCL specification, unlike some other specification that I have read, is fairly easy to read. There are examples in there that you can use to get started, to get some intuition about how things work. And so it's generally quite accessible.
Right.
And one quick thing I would add to that as well, that like the SYCL working group has been trying to work hard to try and be more kind of visible in terms of what we're doing. And one of the things that we do now is the ratified specifications are now available on the Kronos GitHub, which means that when you're looking through the SYCL specification, if you see anything that maybe you're not sure of, or you maybe have a suggestion about, you can post comments or suggestions there, and then we can always make kind of clarifications to the spec to kind of make things clearer.
Yeah, for sure. And on that note as well, something future looking towards kind of a usability aspect of things. We're hoping that in the future, and we can't really give concrete dates for any of this yet, but we're hoping to be able to put specifications online in forms that aren't either LaTeX source files or PDF files, but something that's a little more web friendly. So hopefully that will happen before too long.
Great. I would just say that we are trying to get things up on something like Compiler Explorer or something like CPP reference. And if people would like to help us with that, please volunteer and let us know. And in so doing, learn. That's another project on SYCL that you might be interested in helping us. Okay. I think we're now at the top of the hour, and we're ready to restart the next set of talks. This is our last section, I believe. Rod, how are we doing on restarting?
Yeah, thanks, Michael. I'll start putting the video on now.
Now, let's talk about one of the extensions introduced in DPC++, Unified Shared Memory. SYCL provides two abstractions for managing memory, buffers and images. Buffers describes 1, 2, or 3-dimensional arrays. Images are special type of buffers with additional features specific to image processing. Buffers and images are powerful abstractions that solve many problems for a programmer. For example, dependencies between kernels. However, programming with buffers requires to change all interfaces in existing code to accept buffers or accessors, which may be time-consuming. DPC++ adds one more important memory management option, Unified Shared Memory, USM. It is a pointer-based approach that should be familiar to C++ programmers using malloc on U for memory allocation. It provides much easier integration with existing C++ code, since with USM we still operate with pointers and have a desired level of control. Let's talk about USM in more details. USM requires a device that supports a unified virtual address space. It means that any pointer value returned by a USM allocation function on the host will be a valid pointer on the device. It is not required to map a pointer on the host to a device version. There are three types of allocation in USM: device, host, and shared. All types of allocations are performed on the host. Device allocations are allocations in device local memory. You can read and write to this memory on device, but you can't directly access it from the host. In order to move data between regular allocations in host memory and device allocations, you need to use explicit copy operations like memcpy. Host allocations are allocations in host memory. You can access it on the host and on a device, so the same pointer value is valid both in host code and in device kernel. Note that the data always comes from the host memory. When you access a host allocation type pointer in device kernel, the data is sent from the host to the device over a bus, such as PCI Express. The data does not migrate from the host to device local memory. Shared allocations are allocations that are accessible on both the host and the device. They are similar to host allocations, but the difference is that data can migrate between host memory and device local memory. Once the migration happened, the access on device to the data is much faster, since the device local memory is used instead of remote host memory. This is implemented inside the DPC++ runtime and lower-level drivers. Based on allocation type, there are two data movement strategies in USM: explicit and implicit. Different allocation types map to different strategies. Explicit data movement with USM is realized with device allocations and an MCPI member function in the queue and handler classes. This function is specific to DPC++. The programmer enqueues the MCPI operations to transfer data from the host to the device or from the device to the host. Implicit data movement with USM is realized with host and shared allocations. In that case, there is no need to explicitly enqueue the MCPI to move data between host and device. You can simply access pointers inside the kernel, and the required data movements is done automatically. This greatly simplifies porting existing codes to DPC++. Simply replace any malloc on U with the appropriate DPC++ USM allocation function, and everything should just work. Let's take a look on a simple code showing the explicit data movement. We consider that we are using a SYCL namespace by default. As usual, we create a queue with default constructor, so a default device selector is used. We create a host array on stack and then initialize it. We also allocate a memory on device via malloc device and getting a pointer device array. There is a kernel that operates on a device allocation using this pointer. Data is copied explicitly between host array and device array before and after the kernel executes using MCPI operations. We call wait to be sure that the copy to the device has completed before the kernel executes, and to be on the safe side that the kernel has completed before the data is copied back to the host. In this example, we create two arrays, host array and shared array, with a host and shared allocations. We can initialize host array in the host code since it is a valid pointer on both host and device. It can be also directly accessed inside the kernel, performing remote reads of the data. The runtime ensures that shared array is available on the device before the kernel accesses it, and that it is moved back when it is later read by the host code, all without explicit programmer control. Let's talk about pros and cons of explicit and implicit data movement and understand where we may benefit. The main advantage of explicit data movement is that the programmer has full control and can decide when data should be transferred between different memories. This is important because overlapping computation with data transfer can be essential to get the best performance on some hardware. The drawback is that it requires more efforts to specify all data movements and can result in errors. For example, you can transfer an incorrect amount of data, or not all data can be transferred before a kernel begins computing. This can lead to wrong result. This drawback creates a barrier to entry when prototyping or evaluating the computational power of a particular accelerator. Getting all of the data movement correct upfront can be a time-consuming task. Implicit data movement requires less effort to get an application to take advantage of device local memory. Runtime does a lot for us. It reduces the possibility to introduce errors into a program, since the runtime will automatically identify both when data transfers and how much data must be transferred. The drawback of implicit data movement is that the programmer has less or no control over the runtime behavior. In some cases, it may not move data in an optimal way, and we can have a negative impact on program performance. The best strategy for a program can depend on many different factors. Different strategies might be used for different phases of program development. You can mix and match the explicit and implicit methods for different pieces of a program. For example, start with implicit data movement to simplify porting an application to a new device. As you begin tuning the application for performance, you might start replacing implicit data movement with explicit in performance-critical parts of the code. Now, let's compare the code written using buffer abstraction module and USM. Here we have a buffer implementation. First, we create an array and initialize it. Then, we need to create a buffer and instantiate accessor in order to access the data from the device code. We are doing an implicit synchronization by introducing a scope, so buffers are destructed at this point and execution of the kernel is finished. Here is the corresponding USM code flow with implicit data movement. We start with memory allocation and then using the return pointer inside the kernel with no need in accessors. We need to explicitly synchronize before accessing the data. In DPC++, kernels can be viewed as asynchronous tasks that are submitted for execution. These tasks must be submitted to a queue where they are scheduled for execution on a device. In many cases, kernels must execute in a specific order so that the correct result is computed. With buffer abstraction model, there is no need in explicit task scheduling because the directed acycling graph is built under the hood automatically based on common group objects that specifies a task and its dependencies. So runtime cares about the kernel's execution order for us. With USM, this graph is not built automatically, but there are still several options to control the task scheduling. Note that queues are out of order in SYCL. As an alternative, you can use in-order queues, which are DPC++ extensions, and solve possible dependencies issues, but this is limiting the performance. With USM, we explicitly ordering tasks based on the computations that occur rather than on the data accessed by the computations. One option is to synchronize through the host by explicitly calling the wait method on the event. This forces the runtime to wait for the task that generated the event to finish executing before host program execution may continue. You can also call wait on a queue object, which would block execution on the host until all enqueued tasks have completed. This can be useful if you don't want to keep track of all the events returned by enqueued tasks. The second way events can be used is via depends-on function. The handler class contains a method named depends-on. This method accepts either a single event or a vector of events and informs the runtime that a common group being submitted requires the specified events to complete before the specified task may execute. Finally, let's discuss the question how to choose the best data management strategy for your needs. Actually, selecting the data management strategy for your applications is a matter of personal preference. You may start with one strategy and then switch to another. However, there are a few useful guidelines to help you pick a strategy that will serve your needs. First, you need to choose between explicit or implicit data movement. This greatly affects what needs to be done to bring a program into DPC++. We already discussed pros and cons of different strategies. If you are porting an existing C or C++ program that uses pointers or CUDA code, USM might be an easier path. Another question to ask is how you would like to express your dependencies between kernels. If you like to think about data dependencies between kernels, choose buffers. If you prefer to think about dependencies as performing one computation before another, choose USM. While using USM pointers, you have also a choice to select the type of queue you want to use. In-order queues are simple and intuitive, but they constrain the runtime and may limit performance. Out-of-order queues are more complex, but they give the runtime more freedom to reorder and overlap execution. The out-of-order queue is the right choice if your program will have complex dependencies between kernels. If you simply want to run many kernels one by one, then the in-order queue will be a better option for you. Thank you for your attention, and now we are open for Q&A.
Hello, my name is Ronan Kerriel, and I work at the Xilinx Research Labs, and I'm also the editor for the specification of the SYCL standard. I will present. Hello, my name is Ronan Kerriel, and I work at the Xilinx Research Labs, and I'm also the editor for the specification of the SYCL standard. I will present you some extensions that we have for the Xilinx FPGAs and for the Versal ACAP chip in the SYCL open source implementation. The problem we have nowadays when you want to program some application on a real platform is that you have to address all the accelerators you have in your systems. And for example, on our Versal platform, we have several different CPUs. You have an FPGA, and inside the FPGA, you could also have some specific overlay architectures you would want to program with some, for example, microblaze CPU to program and things like that. But more interestingly, we have our coarse-grained reconfigurable architecture where you have an array of cores and each core has its own memory. So it's a complex stuff to program, and if you want to scale this at the data center or HPC level, it will become more and more complex to deal with OpenMP, MPI, and things like that. So we really need a programming model, but fortunately, the good news is that with modern C++ and specifically with SYCL DSL, we can probably address some aspects of this. And actually, since SYCL is a pure C++ DSL, probably we can reuse the same tricks we have in C++ to express in some C++ classes more and more DSL to express and to address our problems. For example, you can start with C++20 to program a normal machine, I would say, where you have an homogeneous single memory view, but then you can, in this application, use some C++ parallel libs, such as Cocos, that will allow you to express more stuff in parallel and to control more things. And the Cocos implementation could use C++ SYCL. And to also control more detailed stuff, you can have an architecture libs written in C++ expressing a lot of details. And going down, you could have some domain libraries to, for example, control some machine learning operation or some software-defined radio for 5G, for example, some very specific operators. So probably it's possible to do all that stuff in C++. So that's what we try to do in SYCL with some extensions. So let's start with some FPGA extensions. So the most common optimization we can do when we execute, for example, some loops on FPGAs is to use pipelining. So if you consider here a loop with 3 operations, so you read, compute, and write. If you execute it naively on the hardware, you will have some kind of sequential execution of your loop. But if you think about that on FPGA, you have a real implementation in hardware or these operations, they will be unused most of the time. So if you execute the loops in parallel, you can overlap all the different stages and to improve the throughput of your loop. So what we've done in SYCL is to introduce this green line. So when you have in a kernel some loops, you can express the fact that you want the loop body to be executed in a pipeline way just by wrapping the body with this pipeline decorator, which is pure C++. So it's not an alien pragma or an attribute as it can be provided by some other tools. The fact that it's just pure C++ means that you can implement it in a very straightforward way. For example, pipeline here is just a generic lambda taking some code, and your pipeline operation just execute your code, but before it executes this specific intrinsics, where the syntax is not important here, but it's just a way to express to our backend that we want to use some pipelining here. And since since we want this code still be compatible with some other SYCL implementation or to run on the CPU when you do not have a real FPGA, then the intrinsic itself, when you have a real SYCL device, is something not very important here. But most important is that when you are not in this SYCL extension, then your intrinsic for spec pipeline is just an empty operation, so it does nothing. So it's still compatible with normal SYCL implementation. Another interesting thing with FPGA is that you can partition memory. Yeah, a common problem for parallel programming since the 70s is that when you execute things in parallel, you will have probably some conflicts on the memory in your system. But the good news is that in the FPGA world, everything is reconfigurable, even the memory architecture. For example, if you have a 1D array of 16 elements, instead of having only one memory to store this element, you could decide, for example, to have a cyclic partitioning to distribute all your 16 elements on 4 memory banks in a cyclic way or in a block way, or even go wild and have one memory per element of your array. Of course, it will require quite a lot more hardware, but the performance will be quite higher in some application. But the same way, we can express this also in pure C++ by just introducing some new data types, new arrays with some obviously some types, but also some, for example, some block size and some partition parameters. So you will have A that will be a partition array at the end. So it's directly in the C++ types. So it's a portable C++, and then because you can run this on normal CPUs or on some other accelerators that does not support this extension, because you can always provide some implementation which are equivalent to a stud array. And you can do some introspection on this if you want to do some complex metaprogramming, which is not possible to do if you use some more traditional approaches, which are, for example, using some pragmas in some tools, or to use attributes in, for example, like in the Xilinx OpenCL C implementation. So for example, in the case of the pragma, the pragma description is not directly attached to the declaration that makes the code harder to think about, and it's not compatible with template metaprogramming in most of the cases. But at the end, what is interesting is with SYCL, you can generate some code that will be ingested by our backend compilers and just generate some kernels for the SYCL kernels, and it will automatically generate all the infrastructure to run them and to generate the bit stream that will describe the real FPGA layout for the real execution. For example, here our kernel is the yellow part on the picture. Recently, Intel published an open source SYCL extension, which are pipes. And that's interesting because it extends some FPGA abstraction for pipes we have already, for example, in the Intel Altera channels or in the Xilinx HLS implementation as axis stream, but with some modern C++ flavor. So it simplifies what we have pushed in some deprecated SYCL implementation before. So the idea is to introduce a new data types that will represent some communication channels. So the pipe here will be a pipe of integers plus some name to identify the pipe. And then to use it, for example, from the FPGA, you create a queue for your FPGA, and you launch a single task on the FPGA. Here it's forever. You will write on your pipe something produced by some produce function, and you will create another task that will read data from the pipe to process them on the FPGA. So you can see basically in 3 lines or 4 lines, you can create some very simple data flow programs that will run on the FPGAs with 2 kernels, with a producer and a consumer. Even more interesting, you can have some specific pipes allowing you to address the real hardware on your system. For example, imagine you have somewhere from your vendor some hardware description describing some Ethernet pipes to read and write from your Ethernet NIC. So in the user application here, you can create a NIC pipe named sniffing using the platform Ethernet with so it will be used to transfer some data between the FPGA and the host, and the data will be Ethernet packet, and you can have up to 1,000 packets in flight. So the idea here is to use the FPGA to capture the Ethernet packet, to do some filtering, and to forward the interesting packets to the CPU where they will be further analyzed. So for this, you just launch on your FPGA queue a single task that will read forever some Ethernet packets, and will just filter them. And if it's an interesting Ethernet packet, it will forward it to the NIC pipe here. And the NIC pipe is actually used on the host side, so it's executed on the host because there is no queue involved. And on the host, you will just analyze what you read from the pipe. So it's very terse syntax. And since everything is static, you can generate some very efficient code from this. We've implemented this in SYCL on CPU for now by using Boost Fiber's buffer channel. And what is nice is in C++20, we have this new concept of ranges that bring some similar data flow programming style. So which means that for some spatial architectures, we can probably implement all these stud ranges as this kind of pipe operation. Okay, I won't say more on the FPGA part, but now I will talk a little bit more about the ACAP extensions. So the ACAP is for our Versal Adaptive Compute Acceleration Platform. And in this platform, we have a coarse grain reconfigurable arrays with an AI engine. So the architecture is you have a lot of cores with their own memories and some specific network on chip to interconnect everything, and you have also an FPGA on board interconnected to this CG array. That means that we need a framework to program everything in the at the same time in a single view, so in a single source approach. So that's why we have developed this AK++ DSL on top of SYCL. So the idea is just to extend the basic SYCL object by templating them with 2D coordinates. For example, so the platform, the devices are the kernels are recycled as it, but now the cores are represented by tiles and with some XY coordinates, and even the memory of the tiles are also expressed in the programming model also in a XY templated way. And you can also access to the switches to program them inside the tile to reconfigure your network as you want for your application. So how to program this? So the idea is to use a device like the SYCL-like devices to template them by some layout. For example, here for our VC1902 chip that will express the X and Y geometry and things like that. And so you can run, for example, some programs, and this program is as I said, a templated tile by XY. And here in our Hello World program, we just want to express our X and Y coordinates. So we can probably run this like that. So each tile is expressing its own coordinate, and it's run on my CPU in emulation mode on my laptop here. So you can see it runs on different stud thread in parallel. So you can see that you have some race condition, obviously, but that's normal because we run everything in parallel. And you should not write code like this, of course. Okay, to help debugging, we have some graphics libraries because it's very useful to use graphics for debugging. And it's small GNOME GTK application. Under the hood, we also use the MDSpan proposal to represent arrays and tilings and things like that. So, for example, you can run simple program like this to represent all the pixel and the tiles. So how to program this? So the same program, so we had 2x3 tiles, so we can express arbitrary layout in our programming model. We can use the graphics tool. And here we run a Mandelbrot program, but also with specific explicit memory content. So in our programming model, we can weave in by using metaprogramming the program part of the AI engine content with the memory part of the content. And you can express both the program and the memory part in our programming model by using some templated data types. The memory here is just a pixel plane, which is a small array, and it's actually the same for all the tiles. And for the Mandelbrot computation itself, so we use X and Y coordinates to change a little bit the computation, so to distribute the work on our tiles. And by using metaprogramming, we introduce some new member function to access to our own memory. So it's accessed by this tmem alias. So then in the code, when we access, for example, for the pixel jy in plane here through m, it will access actually this memory tile in a type-safe way. So that's interesting that if there is no for a given tile, these data types, you will have an error compilation and not a runtime error. Okay. More interesting is that for some serious application, for example, you want to execute some HPC-like stuff such as PDE, and here we want to have a demo that uses a simple first-order differentiation scheme because it's easier to fit on one slide. And the interesting part, if you distribute the content by block, it only requires some direct for neighbor communication. And that's something, if you think about it, which is not possible to do on GPU without going through the global memory, because the architecture and the priming model is organized like that. That means that you have some high latency and you use a lot of energy for this. But for our AI engine, CGRA, it should be perfect because we have in the hardware a way to address to the memory of our neighbor, so it should provide low latency and low energy. So the application, the full application in the sequential way fit on one slide. So it's three 2D nested loops. And here we use this Fortran-esque syntax because we use mdspan from the future ISO C++ to express our code. And we will focus on this yellow loopness, this yellow operation. So if we distribute, for example, W by block on our tiles, then when you want to access to WJ 1 + 1, 1 + 1 might be stored actually in the neighborhood memory. So that's why you have this problem of how to access to these elements that might be at your neighbor's memory. So either in your hardware, you can directly read them, but it might complex the loopness, or you could extend all, for example, here, the W with an overlapping zone or ghost zone, halo zone, or whatever. There are different names for that to take into account this and to prefetch them, the data, by using some DME hardware or something like that. Okay, perhaps you can just run the program to express a little bit what's happening here. So we have our domain distributed by tiles. So you can, in the graphics interface, so you can see all the tile coordinates. And you can run the demo here. It's on my laptop in CPU emulation mode, so it's quite fast enough. And so here I have some different depth in my shallow water, so I have a different speed. I've had in a few for fun, a few boundary condition here with some holes, so you can see the diffraction of the waves in the water happening here. So, well, I don't know how it renders on the video recording, which is only 4 frames per second, but I hope it will be smooth enough for you to see what's happening here. Anyway, so the idea, the problem is that so in each tile you need to communicate some data. So I will just show quickly how it can be done in our framework. So as seen previously, so you have this mem alias to access to your own memory. but we have also the mem up, mem right, mem left, and so on to access to all the neighbors' memories. And you have, for example, if you are not a module on the top of the array, then there is a neighbors up. So you can just access to these neighbor memories and to do some transfers, for example, writing some content and to write it into your above neighbors and so on. And we expose also some hardware features such as barriers between tiles to avoid data races in the various tiles. Okay. What is interesting in this pure C++ programming model is that since you in SYCL you can always run everything on CPU in emulation mode, then it's very useful to debug directly on the host, and also if you do not have yet a device implementation running. So you can use a normal debugger, and this programming model on the host, one thread is run on stud thread, obviously, but each AI engine tile core or each GPU work item, FPGA work item runs in a stud thread on CPU, so you can debug this in GDB, which is scriptable in Python. You can use normal memory checkers such as Valgrind or UBSAN or whatever. And all these tools are also scriptable in Python. So you can really develop your own debugging tools to ease that. And what is amazing actually is that since we have a direct mapping from some hardware features into normal C++ stud thread plus locks plus condition variables and things like that, you can actually detect on the CPU some race condition related to some hardware features. So that's pretty cool. It would be impossible to debug this kind of code otherwise. Well, and you can use obviously a lot of classical C++ debug and use graphics things and so on. So to conclude, so obviously SYCL is a very interesting programming model providing some foundational base for modern single source heterogeneous computing. And that's important because you have to focus on the whole system, which means system-wide compute language like SYCL. And single source allows you to address the full application and enable generic libraries to address both the host part and the device part, because at the end, that's what you have to optimize in the real application. And now the heterogeneous platforms are really heterogeneous with a lot of wild accelerators. And SYCL is used at Xilinx to develop and to experiment this DSL extension on top of SYCL for spatial computing for our Xilinx FPGAs or ACAP, coarse-grained reconfigurable arrays. And what is interesting is that we can express in very modern C++20 ways some explicit detail. I mean, you can have an explicit programming models that allow us to reach a bare metal efficiency. For example, we can provide some MD-span-based abstraction on top of DMAs or to express a multi-level memory hierarchies or overlay architecture. So it's pretty neat. And since it's all a pure modern C++ DSL, well, you can directly emulate your target on CPU and to debug and even to co-design your application, your system, to experiment with some new architecture details that you have not implemented yet on the real hardware and to see how it would be easy or hard to program and how the performance would be. So it's cool to have this, to rely on this host device backend execution mode of SYCL just for this. That's it. If you have some questions, I think you can ask them online. Thank you for your time.
Okay, great. Before we move back to the panel session. There's a little link that I've put up on the screen. If you were doing the exercises on Monday, there's an additional USM, Unified Shared Memory exercise that you can do over there. So if you want to give that a go, you can. But in the meantime, I will hand over to Michael to kick off the rest of the.
Yep, I got it. Thank you. Hi, everybody. Welcome back. Welcome to everyone who stayed. This was actually probably the meat of the biggest meat of the part that talks about the future of SYCL. And as a result, there is going to be a lot of stuff you saw a lot of stuff that is coming in much greater detail. So we do have a couple of questions, and I want to see if we can get them in before people drop off. The first question is from Zhimeng Jin. He asked about event profiling. Is info : event profiling : command _ queued available in the SYCL specification? He noted that this was in 1.2, but has been removed in 1.2.1. And so he's looking for some justification. So I think, Gordon, you might have already answered, so maybe you can summarize that for people.
Yeah, sure. So this is one of the options for querying profile information on the events you get back from a command group submission. So between 1.2 and 1.2.1, it was decided to remove one of them. That's the command queued one. The reason for this is that it was found that because there's not a clear mapping of SYCL command groups to the backend commands that get enqueued, and the specific commands that the backend enqueues are kind of implementation defined. It was very difficult for implementations to provide a useful value for that query. So we took that one out. There is still 3 other variants of that for when the command group's submitted, when it starts and when it ends.
Okay. Thank you. Anyone else want to add to that? I might point out that we are building the SYCL 2020 reference card, and when it does become available for the provisional, we're going to make it downloadable. So expect that in about a couple of months. Next question comes from Nikolai T. Is it possible to determine memory access in device kernels via SPEAR, or maybe another mechanism through creation of SYCL integration header? What memory access using read, write, or discard and their combination, then to implicitly configure accessors or USM shared memory copying mechanism, and to configure buffers weighting graph. So I think we need a little bit more clarification, but let's assume that, is this a...
So I can take a stab at this, Michael.
Yeah, go ahead.
I think the question is asking if you just had a regular C++ program that has its data structures allocated in normal C++ ways, and you wrote a SYCL kernel that then tried to access that memory, could a sufficiently smart compiler figure out what memory you were accessing, and then either automatically or in a guided fashion let you know what things need to be translated either into USM allocations or SYCL buffers? I think that's what the question might be asking. And that would be a great thing if it could do, but that's a very hard problem to solve, as it winds up looking a whole lot like the general pointer aliasing problem that compilers have been dealing with for decades as they try to automatically parallelize programs. I wouldn't expect a compiler to be able to do this anytime soon, but what you might be able to do is be able to use some sort of performance analyzer or analysis tool that can insert dynamic instrumentation to try to help you figure out what data needs to be accessed on the device and then let you either translate it into a SYCL buffer or a USM pointer.
Yeah, go ahead, Gordon. Yeah.
Yeah, I think I definitely agree with that, and I think there's potentially opportunity there for like static analyzer tools to be able to look at a SYCL kernel and perhaps give you warnings if you're maybe not using the most efficient like access modes and that kind of thing, to kind of maybe suggest different modes for your kernel. But yeah, I'm not sure if it would be possible to be able to rely entirely on a compiler to do all that for you. It's not. I don't think it's always possible to deduce that in all cases.
Yeah,
Very difficult problem to solve.
I think you're right then that the best path forward on this is some combination of static analyzers and dynamic instrumentation to cover the cases where the static analyzers just can't do it.
Right.
Yeah.
So maybe Michael's tired. That's something for the analyzer advisor for the future.
Yeah, feedback noted.
Yeah, feedback. Yeah. All right. Joachim Myers says, and anything else on that topic? Anyone would like to add? If not, then we have one more question. Joachim Meyer asks, can we expect some FPGA optimized SYCL libraries to come and be longer supported than the TensorFlow backend mentioned earlier? Is there anything usable right now? That's a good question. Optimizing for SYCL FPGA libraries. Go ahead, Renan, please.
Yeah. So the TensorFlow library we've experimented, several years ago already. We had some problem with that library because it was developed with a GPU mindset. So at the end, if you just port directly the code and you execute it on FPGA, you will just have bad performance and a lot of other things like that. But that said, obviously, there will be some libraries for FPGA in SYCL, and just for a simple reason is that since SYCL is just C++, that is great because that means that you can just recycle all your libraries available from Force, OpenCL, or whatever directly into SYCL. So that's I think a great advantage of the interoperability mode of SYCL, just to reuse existing libraries. But obviously, there will be probably a lot of libraries written specially in SYCL for FPGAs in the future.
Great. Anyone else like to chime in on this? I think certainly growing the ecosystem is very big. Is very big on all of our minds. And CoPlay had done it with some of the SYCL libraries, and now one DNN, one API is growing and contribute with a lot of contributions from Intel and from other people. So I think that's definitely something that and definitely now we got a third direction that is grow your FPGA libraries. So that it helps people to do their migrations. Okay. Anyone else like to add to that?
Hey, Michael, just a brief note. We actually will have FPGA libraries as part of MKL.
Oh, great. Wonderful.
Some functions will be FPGA enabled, yes.
Okay, thank you. Thank you, Michael. Okay. So we're coming down to the end of the live stream. Let me see. We got about 5 minutes left. And I want to see if any of the panelists wants to add say any last words. So let's start with Renan, going across the screen. Renan, any last words before we close?
Well, I think SYCL is a great opportunity for all this heterogeneous computing, and that's great to have some open standard for this. Just providing a lot of new stuff for C++. And what is great for SYCL is this interoperability modes with a lot of other frameworks. So we can just interconnect and build on top of what have been done by other people. And also the host direct execution of SYCL code is an amazing feature to help debugging applications and to introduce people to these very complex architectures that will pop up even more in the future.
Great, thank you. Next is Gordon Brown. Any last words, Gordon?
The one thing I'd mention is that the SYCL working group is always looking for feedback from developers about what they like and what you'd like to see going forward. So we encourage people to try and get involved as much as they can. There's the public GitHubs on Khronos, and I think there's also a Khronos Slack channel that's on Khronos website, where people can get involved and suggest things. And as we go forward, if once we have more announcements, then we look forward to hearing and seeing people's feedback from that and developing the ecosystem further.
I'll just point out that a lot of those links are on the second last slide of my talk.
Thanks, man.
Yeah, thank you. Next up is Axel Alpe. Any last words?
So yeah, as Gordon said, it's very important for us to have feedback, and there's also a GitHub repository where some of the proposals that we have talked about, like USM and so on, can already be checked on by other people, and I guess we can post that in the Slack, the link. And yeah, so please play around with the stuff, see if you have any feedback, and yeah, we will be very grateful for that.
Thank you, Axel. On the stream, Arben pointed out that about the SYCL spec, that it would be great if there are more examples showing use cases of the various features. For example, an example on using stream or a pointer to an example would be great. And I think that's something we should talk about more, about how to create much better examples. And much more examples, sorry. Next one is James Broadman. Go ahead, James, last words.
Yeah, I hope everyone learned a lot and is excited to go out and try SYCL. And after they have some experience with it, lets us know what they like and what they think could use improvement.
Great, thank you. When you said tricycle, it sounded like tricycle, but I know what you meant.
Thank you, James.
Okay, next up is Michael Steyer. Go ahead, Michael.
Yeah, I'm actually really looking forward to see an increasing adoption of SYCL also in the HPC space, and I'm really curious to see picking up adoption, especially on top 500 machines where people run SYCL for large-scale number crunching.
Great. Thank you, Michael. Next up is Igor. Go ahead, Igor.
I just want to thank all of attendees, which spent the whole 2 days, right, on learning SYCL basics and the implementations. So, and I want to thank you for your continuous feedback and looking forward to hear even more. So, but it's now quite easy to try different SYCL implementations. So just try it and provide your feedback, which can help us make a SYCL even better and continue the development of new features and all this stuff which we really need for heterogeneous programming. So thanks.
Great, thank you, Igor. So at this point, I'd like to hand you back to my host, Rod Burns, who will have the final words. I'm Michael Wong. Thank you very much for joining this live talk. It's been great. Rod, back to you. Anything last minute things you want to say?
Okay, thanks, Michael. Yeah, I would like to reiterate that and just say thank you, especially to Michael for chairing the panel, and to Ronan, Gordon, Axel, James, Mikael, and Igor for joining us as well. and thanks for joining us, and have a good evening. Thanks a lot.